All right, so I finished my general announcements. Not really a whole lot to say because the only thing being collected this week was collected on Monday. The 5.2 work, that's dead today. The quiz, the take-home quiz will be passed back tomorrow. Retakes available for a week. Okay. Students were asked to complete 5.39. The other two problems we more or less got through yesterday. Students were encouraged to complete those problems on your own time. And the answer keys were available both on the video recording as well as the Canvas notes. Okay. So getting down to the bottom, okay, you're asked, is she correct? In a word, is she correct? Yes, she's correct. Okay, now the way in which you decide to argue that is totally up to you. So what I'm going to show you is I have answers that are written both in words, but are also written sort of in notation, kind of a lazy mathematician way of doing it. So you can say to me, at first, there are 26 of 52 cards, which is 50% black. Or you could say to me, the probability of black, and I don't even care if you don't say at the start. If you just say probability of black is 26 out of 52, that's saying the same thing. You could then say to me, but after removing 10 cards, 26 of 42 of them are black, which is 61.9%. Or in notation, you could write this. The probability of black given 10 were removed. That is a conditional probability. It's the probability of black, but it's given some extra information. Okay. And that's 26 out of 42. And then you can point out, so a black card is more likely after 10 cards have been removed, or you can literally compare those numbers and point out, look, 26 out of 52 is less than 26 out of 42. So pick your poison. I don't care. You want to tell it to me in words? Green. If you want to use notation to explain your thought process, blue. But I'm telling you, I have the same mentality of the people who are in charge of grading your AP exams. They want you to get the points. You're human. Put the information on the page in your own style. Okay. If the information's there, you can credit for the thought. Okay. By the way, if she had been drawing with replacement, so if she had been putting the cards back every single time, okay, or in this case, if you were putting the cards back every single time, then I would actually say the friend is wrong. You're 100% wrong. I don't care that I got 10 red cards in a row. If I keep putting the card back and reshuffling the deck, every time I reach into that deck, there's a 26 out of 52 chance of getting a black card. It doesn't matter that I got a bunch of reds in a row. Okay. Let me give you one other example of conditional probability that I think tons of people mess up all the time. Okay. If I asked you, what is the probability you flip a coin and you get heads? 50%. If I asked you, what's the probability when you flip a fair coin, you get 5 heads in a row? That's a really small number. It's rare for a fair coin to flip 5 times in a row and gets heads. It happens less than 5% of the time. That's our standard of rare. Okay. However, if I say to you, I just flipped this coin 4 times in a row and got heads, what's the probability I'm going to get 5 heads in a row? That's very different than asking, what's the probability of 5 heads in a row? That's asking, what's the probability of 5 heads in a row given you already have 4? And the answer to that question is 50%. Okay. I don't care that you got 4 heads in a row already. The probability you're now going to get that 5th one is still 50%. So that is the difference between independent probabilities, 0.5 times 0.5 times 0.5 times 0.5, 5 times, and conditional probabilities. You're still asking about the probability of 5 heads in a row, but you've been given the extra information that you already have 4. So it's a completely different calculation, or in this case, number. Okay? All right. Questions before I ask you to turn the page? All right, turn the page. To help you be confident in what you are doing after you've read the problem, I've given you not the work shown, but the answers to A and B. You've got 4 minutes to get as far as you can. If you're not able to finish all of the problem, please don't let that be a stressor. Just get as far as you can into 5.310. Show a little bit of work, give me the answer. Go. All right, so I gave students 4 minutes to work on 5.310. I'm going to basically do the same thing for 5.311. This alters the situation by now bringing a conditional format. Okay, it brings in the idea that every time you make a good serve, you kind of feel more confident. You have a better chance of making your next one. Every time you miss a serve, you kind of feel less confident. You kind of lose probability of making the next one. Okay, so again, don't stress if you're not able to finish. I'm going to tack on an extra minute because this one's a bit more challenging. I've given you the first 2 answers without the work shown. See how far you can get. All right. So I was asked to explain number one. Remember, the problem tells you that every time you make a serve, you kind of become more confident. Your chance of going up, of making a serve goes up 10%. So the first serve, you have a 70% chance. But the moment you make it, you now are not at a 70-30 breakdown. You're now at an 80-20 breakdown for your next serve. And so there's an 80% chance you're going to make the second one. But the moment you make that one, you get more confident, and your chance is no longer 80-20, it's now 90-10. And so your chance of making the third serve is 90%. So it literally counts up 70, 80, 90. Now, this is strongly related to C. So I'm going to go right to C just because they're so related. In C, it says, what's the probability you get 10 good ones in a row? Well, the first serve is still 70. But the moment you make it, the second one is 80. But the moment you make that, you're now at 90. But the problem stipulates you can't go to 100%. Nobody's going to be perfect. You're capped at 90. So the first serve is 70, second serve is 80, and every serve after that, meaning the other 8, you're at 90. Because you make it, you're still at 90. You make it, you're still at 90. You make it, you're still at 90. So it's 70, 80 with 8 90s after that. That's why this is important. Okay? Okay, for the 3 bad serves in a row, I'm going to write some extra notation here. In the beginning, you are at a 70-30 breakdown. Everybody with me? Let me zoom in on that a bit more so it's easier to see. Bear with me here, folks. Okay, so in the beginning, by the way, if you don't need to hear this, still keep quiet because I'm sure plenty of people do. There's a 70-30 breakdown. So there's a 30% chance you're going to miss. So we take a number. But the moment you miss it, you lose a little confidence. And now your chances of making the next one drop to 65, which means your chances of missing have gone up to 35. So your chances of missing the second one are 35. And the moment you miss that one, you lose confidence even more. And your chance of success drops by another 5% to 60. And now you're at 40. And the chances of missing the third one are therefore 40. So it's 30, 35, 40. Think of it this way. If you keep making them, your chance of making keeps going up. That's what C demonstrates. If you keep missing them, then your chances of missing also keep going up. Does that make sense? Okay. Now, the challenge problem is where it gets kind of obnoxious, because with this one, every time you make a serve, your chance goes up. Every time you miss a serve, your chance goes down. So in the beginning, you have a 70-30 chance of making it. But when the moment you make it, you're at 80-20. So you made the first two, 70-80. But then your chances of missing the third one, keep in mind, you just made 2 in a row. So now you go into the third shot at a 90-10 breakdown. So there's a 10% chance you're going to miss it. And the moment you miss that, your breakdown goes from 90-10 to 85-15. So there's a 15% chance you're going to miss that one. But your fourth one's supposed to be good. And by missing this one, you drop to an 80-20 and you make it. So what I will tell you is, I don't want to go through that over and over and over again right now. But if you can make sense of what the heck is going on there, then you understand something that is far more complicated than I would ever throw at you on a quiz or test, or what you'd see on the AP exam. Questions. So let me zoom out here. So we've had a lot of mathematical practice to try to understand the difference between events that are truly independent. So you can just multiply the same numbers over and over again. 30-70, 30-70, 30-70, mismake. Or conditional probabilities, where these numbers fluctuate based on what happened prior. Now we're going to transition to, can we provide a context in which this would actually be used? Okay, so go ahead and turn the page. I'm going to give you all, we'll say, 2 minutes, because this really shouldn't, I don't want you to worry about part F. Don't worry about part F. Just complete A through E. Your answers should look like I provided for A. I want the notation. I want you to practice at least once or twice notation. I keep making it green. For this one time, I want to make the notation blue. Okay? So this is what I want your answers for A through E to look like. Provide the notation that summarizes the question. Provide the fraction for the work. Okay? If you want to get the decimal percentage, that's up to you. But I want the fraction unsimplified. Okay? Take 2 minutes. A through E. Go. All right. So I gave students a couple minutes to get through A through E. The punchline again is part F, which we're going to do now together. Okay? This is, again, how you can use conditional probabilities to compare to flat probabilities to make a decision. It says the probabilities you found in parts A and C should be different. They are. Probability A says the probability of being a male is around 47%. Part C says, if I know you're a liberal, well, then according to this data, the probability you're a male is 41%. Those are more than 5% different. So that is what we would consider different enough that it's significant. Okay. By the way, that's a very loose definition of significance. We'll get more specific with it second semester. Okay. So I would say this means the question says, explain what this implies about the events male and liberal. It means these are dependent events. The probability of being male in general is 47%. But if I know you're liberal, knowing that alters the probability you're male. So that is the very definition of dependence. This event affected the probability of that event. That's dependency. Okay. Now, if we keep reading, it says, then explain what the difference in those percentages means. Now, what I will tell you is if you're going to talk about the difference of percentages, you better know what the percentages are. So in the original work up at the top, I just said, give me the fraction. But now you need to start actually, you can't provide the fraction. You can't say that this fraction is different from that fraction. Like, that's not a way of directly comparing fractions unless they happen to have the same denominator. Like, that's the only way that you could directly compare fractions. Okay. But what this actually tells me is if I pick a random person, the chances that they're male is 47%. But if I pick a random person and you tell me extra information about them, you tell me, I know this person is liberal, well, that then tells me, okay, their probability of being a male just went down. Okay. So this implies if a person is a liberal, that person is less likely to be male. That's what that comparison means. Your chances of being male in general is greater than your chances of being male if I know you're a liberal. Before we move to the final thing for the day, I wanted to show you all something because I find this connection kind of interesting. We've now agreed male and liberal are dependent events. I want to go back to question D. It says probability a random student in this group is a liberal male. So you are both liberal and you are a male. It's not a coincidence that I put that question on the paper. We have a simplistic multiplication rule that says if you want to know the probability of male and liberal, just go ahead and multiply them. Now, you all found the probability of being male is 68 out of 143. What is the probability of being liberal? What out of 143? 61. So our simplistic multiplication rule says if you want to know the probability of male and liberal, multiply those probabilities. 68 out of 143 times 61 out of 143. I will guarantee you, whatever the heck that number is not what we found. The multiplication rule does not work for the events male and liberal. Why? Because they're dependent. And this rule of multiplication requires that the events be independent. They're not. They're dependent. The fact that you're a liberal implies there's a different probability you're male. So watch what happens. Okay? If you realize dependence and you want to find the probability of male and liberal, you take the probability of male and you don't just multiply by the probability of liberal. You multiply by the probability of liberal given the new information that you're male. You multiply it still m times L, but you have to kind of conditionalize the probability of L based on the fact that you know you're dealing with a male. This works. This will get us the same answer we got for part D. The probability of male is again 68 out of 143. The probability of liberal given male is 25 out of 68. You all found it intuitively. I didn't tell you to use a formula to get this. And you all got D intuitively. You just read numbers off of a chart. And if you cross multiply these, the 68s go away and you're left with your answer to part D. So the general multiplication rule works, and you have to use the general one here because the events you're talking about are dependent. Questions? Okay, so this page was a light introduction into how you can use conditional probabilities to argue for independence versus dependence. I will say This is something we've already done. This was actually one of the first things I had you all do in the beginning of the year with the M&M lab. It was peanut M&Ms versus milk chocolate M&Ms. And we saw that peanut M&Ms had a higher proportion of yellow. I don't remember what the color was. Okay, so we talked about this already. We just didn't formalize it with this notation. So here's the deal. Like I said, we have one other question I want to get through today. It is not this one. 5.313, as far as I'm concerned, is redundant with 5.312. So I'm going to invite you all on your own time, if you want the extra practice, try 5.313 yourselves. Check Canvas notes. But we're going to end on a very important distinction I want to make sure we're clear on. This is a distinction that a lot of people mess up. Okay? I need you to really separate out the concept of independent, dependent, that's one idea, versus mutually exclusive or not. I'm telling you now, these are two concepts that people love to twist into a pretzel and act like they're the same thing, and they're just not. Independent, dependent is a very different decision than mutually exclusive or not. Okay? That's what I want to try to demonstrate here. All right, we're only going to get through maybe the first four, and then we'll treat the other ones as maybe a warm-up tomorrow. That's probably what we'll do here. Okay? So for each set of events, place the corresponding letter in the box that best represents their relationship. Okay, so let's look at the first pair. We're going to call this just letter A. Runner number 1, 2, 3, 4 wins. Runner 6, 7, 8, 9 wins. So those are two different events. This runner wins, that runner wins. And we want to talk about their probabilities and how they're related. In parentheses, you're told ties are not allowed. The fact that ties are not allowed, can both of these things occur at the same time? No. So they are definitely mutually exclusive. They belong in the first column. Okay, they're mutually exclusive. But that's not the same as deciding are they independent or dependent. Okay, so let's imagine for a moment, I know this is unrealistic, but let's imagine it's a race with 1,000 runners and they're all perfectly equally skilled. Again, very unrealistic, but we're trying to simplify it. That means each of these people in the beginning, before the race starts, they both have a 1 in 1,000 chance of winning. But the moment that race is over, if I tell you that first event happened, runner 1, 2, 3, 4 won. They won. What's the probability that the other runner won? What is it? 0. So knowing that one event occurred has altered the probability of the other one occurring. The moment you know one occurred, you know the other one didn't. So the probability altered, and this is where the pair of A events goes. Okay, let me show you another one. This one's a bit more subjective, but hopefully I can get the room to agree with me here. You own a cat, you own a bird. Okay, those are two separate ideas. So let's say I'm going over to my neighbor who maybe I just moved in the neighborhood, I don't really know them. Is it possible this neighbor that I don't know owns both a cat and a bird? Yes, you can own a cat and a bird at the same time. They are not mutually exclusive. Now, here's where the subjective part comes in. Let's imagine of all people in the US, 18% of them have a cat. Okay. And then you look at the subgroup of people that you know own a bird. So in general, the probability you own a cat is 18%. But now I want to focus on a subgroup. I want to look at a conditional probability. The condition is you own a bird. If you're looking at people who own a bird, would you think the chances that they also own a cat is greater, less than, or probably about the same? Why less than? Because a cat can eat a bird. It's well known cats and birds probably don't get along all that well. So are there people out there that own both? Sure. Are there people that own both and they get along just fine? I'm sure there are. But in general, it makes sense to me intuitively that if you're going to focus on the people that own a bird, they're probably less likely to own a cat because historically those animals don't agree with each other. Does that make sense? Okay. So I would say they are not mutually exclusive. And again, knowing one affects the other. So again, they're dependent. So notice right away, whether you're mutually exclusive or not mutually exclusive, you can be dependent. So knowing that two things are dependent doesn't mean they're mutually exclusive or not. If I say events A and B are dependent, you don't know, well, are they mutually exclusive or not? Let me do two more. Rolling 1 or 2, rolling a divisor of 6. This one's a little mathematically obnoxious, but I couldn't help myself. Let's first agree on something. What are on a 6-sided die, you have the numbers 1, 2, and 6. Which of those numbers evenly divide 6? 2, 3, 1, and 6. There you go. So you got 1, 2, 3, and 6. Only 4 and 5 don't divide 6 evenly. Got it? So the probability of rolling a divisor of 6 is 4 out of 6. The probability of rolling a 1 or a 2 is 2 out of 6. Go back. 2 out of 6. Okay? Those are the probabilities. Now, if I roll a die, let's say I roll a die, and I'm looking at what I rolled. I'm not going to tell you what I rolled, but I'm looking at it. Is it possible that both of those events are true at the same time? Is it possible that I'm looking at the die and I can say both of those things occurred? Yes. What would I need to roll? A 1 or a 2. If I rolled a 1, there you go. Both things happen. So they are not mutually exclusive. Okay. Now, here's where it gets tricky. We actually, to make things a little easier for you, we don't even need this, believe it or not. The probability, let's just call this for our sanity for a moment, event A and B. The probability of A in general is 2 out of 6. Everybody with me? That, by the way, simplifies to 1/3. Let's see does the probability of A get altered if you know B has occurred. Everybody got me? So here's what this looks like. I roll the die and I tell you B occurred. I'm looking at it. I got a divisor of 6. So how many different numbers could it be? 4 different numbers. Now, how many of those numbers would imply A also occurred? Only 2 of them. If I tell you I rolled a divisor of 6, you know I rolled a 1, 2, 3, or 6. But only 2 of those, a 1 or a 2, would be A. So the moment you know B occurred, the chances of A have been altered. Does that make sense? So that combination is, again, dependent. And I did it by comparing probabilities. Last one, and then we're done. You buy a winning lottery ticket. Someone else does too. So I go to 7-Eleven and I buy a ticket and it ends up being the winning ticket. Not that I would have known that at the time. Okay, so I buy a ticket. It's a winning ticket. I don't know that yet, but it's a winning ticket. Somebody else goes to some other location. They buy a ticket. And they also get a winning ticket. My question is, and maybe you don't know enough about the way the lottery works, can that happen? Can my ticket and their ticket both be the winning ticket? Some people are nodding their heads. Are you allowed to split jackpots? Do we know this? It says jackpots are often split. What does that tell you? 2 people can win at the same time. Just because I go to the store and I buy my ticket and I say, I want number 13, 17, 62, 54, whatever, somebody else in some other store can pick those exact same numbers. Just because I pick them doesn't mean they can't. We can pick the same numbers. So we are not mutually exclusive. But my ability to win has nothing to do with their ability to win. We both have the same chance of winning no matter what. I can pick whatever numbers I want. That has nothing to do with what your chances of winning are. Does that make sense? You can still pick a winning ticket. We both have the same chance. So these are independent combinations. They're not mutually exclusive, but they are independent. Okay? All right. We're done. We're going to finish this page as a warm-up tomorrow with C through J. Thanks for watching. Have a good one.